Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Dr. Kyongmin Yo. Uh, Dr. Kyongmin Yo is a research scientist at IBM TJ Watson Research Center. He received his PhD in applied mathematics from Brown University in 2011. Before joining IBM Research in 2013, he was a postdoctoral fellow at Lawrence Berkeley National Lab. Dr. Yeo has been working on a range of research areas from soft matter physics to atmospheric sciences. And since joining IBM Research, his research interest has been focused on hybrid physics statistic models and deep learning for random dynamical systems. Dr. Kyoming, thank you so much for your time today. And with this short introduction, you can start whenever you are ready.
Okay, Juan, thank you for the invitation. And I also would like to thank George for inviting me to give a talk. By the way, Juan, just to make sure, the talk is 1 hour or half an hour?
It's like 1 hour with questions, so maybe you
Okay,
can.
but yeah,
But usually people ask questions in the middle.
because you said two speakers, I thought maybe half and half or 2 hours. Okay, that's fine.
Yeah.
Great.
Okay.
Thank you. Yeah, then let me start. So the topic I'm going to discuss today is mostly like revisiting a good old state estimation problem, but we are looking at it in a little bit different approaches that what it discovered is that if we use super resolution methods when the data is noisy, then sometimes we can get a much better reconstruction of the ground truth state. So this work is done in collaboration with Maggie, Mike, and Segi. So the collaborators are shown here. So we mostly contributed almost equally. Maggie did most of the numerical simulations and the data analysis. Mike and Segi did most of the theoretical derivations, and I just help them a little bit here and there. So let me start from the motivations. So the motivation is really about what to do when you have the noise in the observations. When you have the measurement of any physical process, it is very difficult to reduce or remove the corruption of the observation due to the noise. So this is one example of the velocity field measurement. When they measure the velocity, this is one of the most widely used velocity measurement device called particle tracking velocimetry. Essentially, it captures the position of neutrally buoyant particles with high-speed camera, and then once you can identify locations of the particles, then you can estimate the velocity at a point. So it takes multiple snapshots. And then first we make a grid on the flow field, and then based on the motion of the particles, now we can estimate the average velocity at each of the grid. But as you can imagine, this type of device has a very, very high noise ratio. So that once we have the measurement, sometimes we get the velocity field which looks like a top left corner here. So in this case, we can recover very small scale structures, but the velocity field is so noisy that you cannot really identify what's really going on. And by adjusting the some parameters such as the averaging width and the correlation length, then you can have many different types of velocity measurement. And eventually, by using very large smoothing length, you can get a very smooth velocity field. But at this point, now we can have a better understanding what's going on, but now we lose all the small scale, like a high wave number information. So that the question is that, what should we do? We want to have an estimation of these very small scale structures, but once we try to have small scale structure, then we end up with too much noise. So the ideal scenario would be to use this type of a smooth velocity field and then reconstruct the missing information. So that's where we are interested in the super resolution method. So the super resolution is not really a new or emerging area. The super resolution has been studied for many decades now. The basic idea of classical super resolution method is that let's say we have a process that we are interested in, but we always observe this process with low resolution observation operator. Then the basic idea is that we observe many of these process in time, then we may be able to stitch different information captured in different sequences to reconstruct the high resolution information. So the example shown here is that they have this low resolution image, and then they are collecting many of these low resolution images. In this case, they are collecting 55 frames. And then by stitching some of the information captured by different areas of the high resolution original data, they can reconstruct this high resolution image. So the classical sense, what we are trying to do is that once we have the sequence of this low resolution information, now we can probably come up with this high resolution data by recovering some of the missing informations. Usually it's done by solving the optimization problem shown here. In this optimization problem, Y denotes the low resolution observation, M is an observation operator, and X is the high resolution data we try to recover. And it also depends on the regularizations. So this is the classical way of people looking at super resolution problems. But when it comes to the deep learning time, now the idea is that instead of solving this optimization problem every time, we want to use a neural network to do the job automatically. So that instead of doing it in a runtime, now we replace this runtime optimization to the training time. So that deep learning models usually are very good at capturing some structures in the data. So in this study, they have developed a super resolution models where you can just give one single snapshot, then it's gonna generate a high resolution image of that single snapshot. So so in this example, what they showed is that when they give this very small section of the original data, then this super resolution model can zoom in to this small section to get a better better high resolution data. So if you see here, this bicubic is probably similar to the low resolution information that's provided to the neural network. And then this ESR again on the bottom right corner is the reconstruction by the authors, and you can see that it has a much sharper reconstruction of the image. So there have been many studies about this potential of single image super resolutions. And then naturally, people in physical domain are interested in this super resolution method. So there are very interesting studies that published in 2020. In this case, they actually went on extreme super resolution because in most cases like here, the super resolution we are looking at is 4 times super resolution. But in this study, they are looking at 50 times super resolution problem where they provide only very crude low resolution information, and they eventually refining up to 50 times to high resolution data. And they made a clever method that instead of trying to go from low resolution to high resolution at once, they first have a construction of the medium resolution model, and then using another model that's having this medium resolution to high resolution. So essentially, we have two sequential super resolution models together. And they applied this method to a global scale weather phenomena. So this is the wind field, you know, global scale wind field, and they showed some reconstruction of this high resolution data to the low resolution data to high resolution, and which looks more realistic. And in the study shown on the right, they are also doing this single snapshot super resolution of turbulent flows. And in this case, they are looking at 4 times super resolution. That the left column shows the low resolution data that's fed into the neural network. And they use something called the cycle GAN to reconstruct the high resolution information from this low resolution data. And what's shown on the right is the ground truth. So you can see that the similarity between the reconstructed field and the ground truth field. And what's interesting in this study is that when they computed the statistics from this reconstruction, then if you look at the figure here on the right, this figure shows energy spectrum of a turbulent field. And then the vertical line denoted in here is the cutoff length that essentially what they did is that they compute the whole velocity using the direct numerical simulations, and they remove the high wave number component, and they provide the neural network only on this low wave number components and asking it to give the high resolution information. And the reconstructed energy spectrum is shown as this circles, and you can see that those reconstruction almost collapse with the ground truth, meaning that this is even with this single snapshot models, the super resolution can really recover the missing information in the data. But there's actually one more important things to note, that the super resolution is essentially an ill-posed problem. Once you give low resolution data, and there is an infinite number of ways to reconstruct the high resolution data that satisfies the low resolution information. One example is shown here. On the left-hand side, they gave a like blood image of Obama. Then when they do the reconstruction, it came out to a completely different person. And another study shown on the right, they gave this very low resolution image of a person to the neural network. And then what they have is that they can get multiple different types of high resolution reconstruction, and all of them look very different, but all of them also can satisfy this low resolution image once it is given. So the question here is that if we are trying to looking at the single snapshot super resolutions, then we end up with this uniqueness problems, so that we cannot really find the unique solutions. So what's likely to happen in the physics problems shown on the above is that once you try to reconstruct this high resolution information from single snapshot, you probably can get a high resolution data that satisfies some of the kinematic conditions, such as the divergence free, like mass conservation in case of incompressible flows. But you cannot really have a solution that satisfies a dynamic constraint, such as momentum conservation. So now, to satisfy such kind of a dynamic constraint, now we have to go back to the old ways of doing super resolutions. Probably the way we can do is that we provide multiple snapshots, and then we're trying to reduce the solution space such that the solution of this super resolution satisfies both kinematic and dynamic conditions. So one of the studies shown here is that now they actually did something like the classical super resolution, that during the training time, they provide the multiple snapshots of low resolution data. Here, T is the time that we want to have a high resolution reconstruction, so that they are providing the number of snapshots before and after the time of interest. And then they showed that this type of multiple snapshot reconstruction is better than single snapshot reconstruction. So if you look at the figure on the bottom left, So here, this black line is the energy spectrum of high resolution ground truth. And this purple line is a single energy spectrum from single snapshot super resolution. And this blue line is a multiple snapshot super resolution problem. And you can see that this multiple snapshot single resolution is closer to the ground truth, saying that this having multiple snapshots to incorporate temporal information actually helps in identifying this high resolution ground truth state from the low resolution data. And here's another study that just came out in Journal of Fluid Mechanics. In this study, what they propose is that instead of having single snapshot super resolution, now they are training a neural network by integrating this time matching error. So in this equation, C is a projection of high resolution data onto low resolution grid. And N is a neural network. In this case, they are using convolution neural network. This phi t is time matching operator, like a Navier-Stokes equation, like time discretized Navier-Stokes equation. Then they train this neural network denoted by N by using by minimizing this time matching error. And the result is shown on the right, that they provide the neural network this low resolution data, and then neural network reconstruct this neural network reconstruct the flow field that's shown on this third column. And you can see the similarity between the reconstruction field and the ground truth, while the input data shown in the middle is losing most of the small scale features. So what I found is shown summarized on figure here. In this figure B, the vertical axis is the reconstruction error. Horizontal axis is different types of low resolution projections and Reynolds number. But if you're just looking at this figure, the error plot on here, this green bar is a single image super resolution, and this red is from multiple images, multiple time matching error super resolution, so that you are essentially incorporating this dynamic constraint during the training. Then you can see that the error is decreased when you have this type of time matching information in the training of super resolution. And another thing they found very interesting is that in this case, they now corrupted the data by noise, as shown in this figure. The red dot indicates the random white noise that is superposed on the ground truth data that's on the top. And what they found is they compared the super resolution time evolution of the velocity field using super resolution and just standard data of simulations. And what they found is that when you use super resolutions, you can see that this noise actually decays much faster than when you do the data assimilations, indicating the super resolution actually has a denoising effect. So based on these observations, now we are more interested in the super resolution in terms of the dynamical systems. So super resolution of dynamical system, it can be summarized by this very simple simple sketch. So let's say we have the original system that is evolving in time. Then when you have this super resolution, what usually done is that in the training that we take the high resolution data that's computed from this original system, and we apply some kind of low resolution filter to remove the high resolution data and convert it to low resolution data. Then there is an observer system. Observer system has a same dynamical equation with the original system, but it has additional term that's taking this low resolution information and then try to compare the difference between the reconstruction and this low resolution data and adjust its own dynamics. So this is the typical setup of the a super resolution of dynamical system, or this is a typical setup of data assimilation problems. So in this case, this observer system, this is super resolution observer system, doesn't really have the information of full high resolution velocity field, and it only see a filtered state variable. Then the next question we naturally have is that then what happens when the original system is chaotic? Like we know that Navier-Stokes equation for turbulent flows is chaotic. Then if we want to have a super resolution observer that's trying to reconstruct the high resolution information, then how can it do it when the system is chaotic? Because for chaotic system, we know that even small perturbations in an initial state can result, eventually result in a divergence of two systems, divergence of the two systems after some Lyapunov time scale. So the answer to this question is coming from some very interesting phenomena called chaos synchronization. Chaos synchronization means that when you have two chaotic systems, actually they can get synchronized with each other by exchanging some information. So here is one example. In this case, they are looking at, so this is one of the early papers about chaos synchronization. In this study, they were looking at the Lossler equations. And then they have one Lossler equation, and then they have second Lossler equation that's starting from different initial conditions. But these two Lossler equations shared one of the axes to drive the second Lossler equations, similar to what we have. And then what they found is that under some parametric constraint, now these two different chaotic systems can actually synchronize with each other by exchanging the information of this y-axis. So there are so this inspired many follow-up studies, and there is a very nice review of chaos synchronization in physical reviews. Essentially, what they are looking at is a coupled dynamical system, which that the original system is evolved with its own dynamics, and they have some observer system that's taking the information from this original system with some filters, and then under some certain conditions, these two systems S and X can be synchronized with each other. So then this chaos synchronization seems to also happen in turbulent flows. So this is one of the early studies about this synchronization in turbulent flows. What they did in this study is that, let's say the original system is denoted by Navier-Stokes equation shown here, and they applied some kind of filtering operator denoted by P1 to remove the high resolution information and only retrieve the low resolution data you want. In this case, they applied the spectral filter so that they only recover the low wave number informations. And then there is evolution, there is an diversification for another velocity field W. This W is essentially computing the difference between the high resolution field and the low resolution velocity field. And then the high resolution velocity original system and this observer system shares the information by this low resolution projections. And then what they found is summarized in the figure in here. Essentially, when they computed the perturbations, that's the magnitude of this velocity field W, then what they found is that this perturbation actually decays exponentially fast. And they found that once this low resolution field is contains information 10 to 15 times larger than the Kolmogorov scale, then you can almost exactly recover this missing information with machine accuracy. So here, The left column shows the velocity field of this low resolution observation. And this right column shows the full reconstruction to the ground truth. And you can see that this low left figure misses a lot of small scale structures, which is recovered on the figure on the right. So there is another studies that came out recently, also suggesting that this type of chaos synchronization in turbulent flows has been observed for a wide range of data assimilation problems. So they suggested that this type of chaos synchronization may be the nature of Navier-Stokes rather than the characteristics of data simulation algorithms, and developed a very nice theory to identify the critical length scale for the chaos synchronization to occur. So this is about this type of chaos synchronization has been studied extensively in data assimilation domain, just with a little bit different language. In data assimilation domain, they were interested in the mathematical theoretical convergence properties of this type of super resolution problem. And then there is a pioneering study by TT and his groups that are looking at the convergence of this type of super resolution problems in turbulent flows. In recent studies, they actually showed that when we use this type of super resolution observers for the Navier-Stokes equations, then we can have the convergence that is exponentially fast, and then it converges to the ground truth system with the motion accuracy. So that it means that when you have but these studies in data simulation is mostly are limited to 2D case, and then they also assume that there is no noise in the data. So that under assumption of no noise and 2D, now we can mathematically theoretically show that the observer system can converge to the ground truth exponentially fast. Now, let's go back to the original motivation I explained in the beginning. So we based on in the original motivation, depending on the parameters we choose, we may have different degrees of noise in the data. And one of the questions we have is that where do we want to start from the reconstruction of the ground truth? How can we getting a better estimation of ground truth by using this very noisy high resolution data, or by using this very smooth low resolution data? So we want to have some guideline about choosing the resolutions, we want to work with, so that in this high resolution data, we certainly contain small scale information, but we have very strong corruption of data. In this case, we don't have such corruption in the data, but we don't have any small scale information left. So we want to have some idea about what's the properties of super resolution when you use these different resolutions. And another important question is that there are many studies using super resolution, but most of them are empirical studies that showing some promise of super resolution in state estimation. But the question is that, do we really have any theoretical guarantees of this super resolution method when it's applied to the noise observations? So the motivation of the current study is really coming from these two, that which scale we want to work with, and then whether we can provide some theoretical guarantee of this convergence. So now let me just talk about the problem setup. So here we again looking at the two-dimensional Navier-Stokes equation, and we are looking at something called chromograph flows. That's a two-dimensional Navier-Stokes equation, which is driven by a sinusoidal external force. We are using periodic boundary conditions. Initially, we start the flow field with we start from randomly generated flow field, very small scale behaviors, and as time goes, it evolves to develop some turbulent like velocity field, and we solve this Navier-Stokes equation using pseudo-spectral method with 512 wave numbers. Now we have the observer system. The observer system is essentially same with the ground truth system, like a reference system, but we have one additional term shown on the right. In this additional term, this C is a low resolution projection operator that is defined here. So in a sense, what this operator does is that we have like this big computational domain, and we break down this domain into smaller subdomains. And this operator first compute the average velocity inside of this subdomain, and then distribute this average uniformly inside of the small rectangles. In other words, you applying this operator to high resolution field. Now we have piecewise continuous velocity field that we have piecewise continuous velocity field. And then there are some constraints that this operator should satisfy that's given by some Poincaré equation inequality in the bottom. So essentially, it gives some upper bound of the size of the rectangle size of the subdomain we can have. Here, H is the length of each subdomain, and C is some constant that depends only on the size of the total domain. So here, here we are actually using a uniform size subdomain. So every subdomain has the same size of rectangles, but in theory, it doesn't have to be the same size. So we can have different like a non-uniform subdomain as long as it covers the whole domain. It covers the whole domain, and they are disjoint. And in this case, this observer system is actually solved by a low order method, not the spectral method. In this case, we are using a second order finite element method to solve this observer. The idea is that we want to use the same solver as the one used to generate the data, because in the real case, in real life problems, we don't really know how the data is generated, so we usually end up with using some kind of low-order solver to approximate the ground truth. So to mimic that kind of real-life scenarios, now we generate the data using very high-resolution method, while the low-resolution data, while the observer is solved by a low-order method such as second finite element method. And here, how the noise data is generated. First, we take the high resolution data denoted by U, and then we add white noise denoted by this eta, and then this capital Y is the projection of this noise data onto a low resolution grid. So in other words, we start from the velocity field, which looks like the one on the left. And then we crop the data, which as shown in the middle with white noise, and then the low resolution data we are supplying to the model looks like on the right, so that it is piecewise continuous, and then it has much less noise. But again, you can see that this after this low resolution projection, it's actually very different from this high resolution data, both in terms of the shape as well as in terms of the magnitude. So it has a much smaller range than the original information. So the white noise here, eta, we don't actually constrain it to be Gaussian, but we only make an assumption that this white noise has no mean, so there is no bias in the white noise, and this white noise satisfy some kind of regularity conditions. So the regularity condition we have is shown on the bottom. Essentially, it says that the average noise inside the subdomain is bounded. So this R is a constant that we can choose. It's just a positive constant we can choose. And to make this inequality, to satisfy this inequality, the only condition is that this eta has a finite variance, so that we, as long as this noise satisfies these conditions, then we are fine. So the main results of the study is summarized here. So you don't really need to look at all the details in this theorem, but what we were able to show is that this G, which is the velocity reconstruction from the observer. This velocity reconstruction converges exponentially fast in time into the neighborhood of the original high resolution data, even when we provide a low resolution projection of the corrupted information. But unlike the noise-free super resolution case, now this reconstruction doesn't really converge exactly to the ground truth. Instead, we can have some kind of constant that we call it convergence zone, that's providing a upper bound of the error, so that when the error becomes larger than this convergence zone, then it's going to it's going to converge it to the going towards the neighborhood of the ground truth. But inside of this convergence zone, we don't actually know how the error will behave. So essentially, it says that unlike the noise-free case, when you have the noise in chaotic systems, we still have a convergence, but the convergence is towards a uh, small area around the ground truth. So now let me just talk about the proof of the convergence theorem. So here, this is just a sketch of the proof. I'm not going to go details about this whole proof of the convergence theorem, but here are something interesting to looking at the proof. So if you look at the convergence theorem, we first start from the weak form of the Navier-Stokes equation and the observer equation. And then by subtracting these two, now we can get an equation for the time evolution of the L2 error. So in this equation, this E denotes the error of the estimation. So this is the ground truth minus the estimated velocity. And then this bracket is an inner product. So essentially, this is the first term shows the how the L2 error changes in time when this G starts from different initial condition from U. And then so the basic idea is that if we can bound these terms, then we can find the upper bound of the time evolution of the error. But I am not going to talk about details of all the terms, but what we are interested in is what's happening in this term that contains both the noise and the low resolution velocity field. So that this F is the external forcing, and this capital F is the low resolution feedback that we explain, low resolution feedback to the observer. And then this capital F can be decomposed into several terms. So G is the known external force. And here capital Y is the low resolution data we are supplying to the observer. And this C is a low resolution projection, G is a estimated velocity field, and L here is just a constant that defines the feedback, the magnitude of the feedback force to the observer. So that we can summarize, by decomposing this Y into ground truth and the noise component, now we can this F can be written in terms of the projection of the error with the projection of the noise, then we can projection of noise. Then we can compute the bound of this term, this product as shown here. Okay, here there's actual typo. This is not psi. This should be eta. So that after doing decomposition, now this term is bounded as shown in this equation, and among these terms, we only have one term that has the projection of the noise. Then let's look at how this projection of the noise behaves. So that now we're looking at the inner product of the noise and the error, estimation error, that we can just write it out. And using the regularization property we assumed before, such that here, such that this noise is bounded by, this noise multiplied by some coefficient is bounded by 1. We can derive the upper bound of the inner product as shown here. And after doing some more work, now we can further refine it, that the inner product between low resolution projection and this error is bounded by L2 error with some coefficient. And the coefficient is shown here, that depends on the size of the subdomain as well as the constant that's inversely proportional to the magnitude of the variance of the noise. Then from this term, now we can have these two terms that have the feedback force of the L2 error and the feedback force multiplied by the product of the low resolution projection of the error, noise and the errors. And then at the end of the day, doing a little bit more work, then we can come up with the equation shown on the bottom left, that the time evolution of the L2 error is bounded by the term on the right. And then we after making some assumptions, now what we can show is we can simplify this equation further, such that the time evolution of L2 error, upper bound of time evolution of L2 error is essentially given by this relaxation equation. So solution of this relaxation equation is simply saying that this error is going towards zero with exponentially fast. But this equation is only valid when the L2 error satisfies these conditions, that is used to derive the bound of this projection. So based on by summarizing all of this information, now we can define the zone of convergence. That this zone of convergence is that when the error becomes larger than this zone of convergence, the error will behave this relaxation equation. So that, in other words, this zone of convergence defines the upper bound of the error estimate we have. And the zone of convergence can be summarized by this equation. Again, here, this sigma depends on the size of the subdomain, and inversely proportional to the magnitude of the noise. And this delta is some coefficient we can choose between 0 and 1. So the implication here is that let's assume this statistically homogeneous system on a uniform grid. So we have a system defined on a uniform grid. Something looks like this. And this delta X is the high resolution, the grid size of high resolution information. And then we have the subdomain that looks like these red rectangles. And the size of this subdomain is denoted by H. Then here we define another constant that is compression, that we call it compression ratio C. C is essentially looking at the super resolution ratio, that the size of the subdomain divided by the resolution of high resolution of the ground truth data. And then based on these parameters and assuming a statistically homogeneous system on a uniform grid, now we can derive that now we can show that the zone of convergence that derived from the theory is actually behave something like this. So what you can see in this case is that this omega is the size of the domain, and this delta is some constant we choose during the theorem in the derivation of theorem. Then essentially this size of this zone of convergence is proportional to the sigma, that's the standard deviation of the noise, and inversely proportional to C, that's the compression ratio. So the theorem essentially saying that as the compression ratio gets larger, meaning that as we have a more coarse resolution to the input, as you make the input resolution to observer coarser, then we get a better reconstruction. The error becomes smaller. So that this corollary essentially summarizes what I explained before, that we can get out of the theorem such that the zone of convergence is now proportional to sigma over C. Again, sigma is the standard deviation of the noise, and C is compression ratio. In other words, the upper bound of L to error decrease as the data resolution becomes coarser. So we did numerical experiments to confirm the behaviors. So again, the original system is solved by pseudospectral method with 512 modes, and the observer system solved by a lower order method. And then the noise magnitude is proportional to turbulent kinetic energy and some coefficient zeta. And we run the simulations with different range of parameters such that the viscosity changes from 0.0015 to 0.009, and the noise level is changing from 0, that's noise free, and 1.6, that's the noise is 1.6 times higher than turbulent kinetic energy with a different compression ratio and And this compression ratio decides the number of subdomains, because number of subdomains is simply compression ratio divided by the size of the grid. And the source code to generate the data as well as the super resolution is given in here. So you can download to reproduce the results. So this is the results of the velocity field reconstruction. Here, the parameter we are looking at is that we have the noise that is 1.6 times bigger than turbulent kinetic energy, and the ratio of super resolution is 32 times, meaning that the super resolution subdomain is 32 times larger than the high resolution grid. So shown on the left column is the ground truth, and we start from a random initialization, and after some time, in this case t equal to 8, we have a turbulent looking velocity field. And the data we are supplying to the super resolution model is shown on the second column, where we cropped this ground truth with a white noise. In this case, we just use Gaussian white noise. So the figure on the bottom actually shows the velocity field taken in the middle of the domain. And you see that comparing to the left to the middle, we have very noisy data. And then after getting this noisy data, now we compute the low resolution projections by averaging over the subdomain. And the data we eventually supply to the super resolution model is shown here. That as you can see here, since we are looking at a compression ratio of 32, we lose a lot of small scale information in the data we are supplying to the model. But when you do the reconstruction that's shown on the right, so initial reconstruction field is starting from almost zero velocity field. So the initial condition of this observer system, that's Navier-Stokes equation, is given as the linear interpolation of this low resolution data that's giving us almost zero velocity field. But after some time, you can see that the reconstructed velocity field really is really close to the ground truth. And then when you compare the velocity profile in the center of the domain, that's on the bottom figure, which is also very close to the ground truth. So this figure showed the error plot using different types of different compression ratio. So this the contour is the reconstruction error, that the super resolution minus the velocity estimation. And when you use a compression ratio equal to 1, meaning that we don't do super resolution, but just doing the data assimilation, Newtonian with Newtonian relaxation, then you see that the reconstructed velocity field still has a lot of a noise. But as we increase the compression ratio further, it's going from left to right, also from left to right, then we have much smaller reconstruction error compared to the high resolution case. And this is actually very similar to the recent study that I explained before, that when they use a super resolution method, we have much better noise filtering capability. So this figure essentially shows the time evolution of the error. So that in this case, error is defined by the relative error. So if we take the definition of the zone of convergence and the noise magnitude, then we can eventually define the relative error. Then this relative error is expected to behave like a zeta over c. So again, this zeta is magnitude of noise, c is the compression ratio. So when you look at the time evolution of this error, then what you can see is that we have this exponential convergence of this error to some bound that is consistent with the theoretical predictions. And if you look at the actual behaviors, then on the top, that is c equal to 1, meaning that that's the case where we don't use any super resolutions. But as we increase the compression ratio, then eventually the error is going down. But we still have the exponential convergence. But if we make this compression ratio too big, like 64, then error is going down until 32. Then when it comes to 64, now error is starting to increase. That's because when you go to too large super resolution ratio, eventually the system violates the necessary conditions for the convergence given in the theorem. So for the interest of time, I'm going to skip here. And this figure essentially shows the convergence of error. In this figure, the vertical axis is the relative error, and the horizontal axis is compression ratio, and different lines denote different noise magnitude. So if you look at these figures, then what you can see is that the error actually decrease as we increase the compression ratio as we predicted in the theory. That is, but the rate of decay is actually much slower than what we had in theory. In theoretical predictions, we predicted that the relative error decays as c to the minus 1. But in numerical experiment, we have much slower decay, that relative error decays as c to the minus 1/2. And then one of the reasons we think that we have a much slower decay is because we are using a low resolution solver for the observer. So if you look at the line on the bottom, like in all the cases, the line in the bottom is the reconstruction with zero noise. And we showed in the beginning that when we have observer with zero noise, then it should converge to the ground truth with machine accuracy. So when you solve this g equal to 0 case with spectral pseudo-spectral method, then this error usually converges to 10 to the minus 15. But instead of that, now we have this finite error that is because of the numerical error we have. So in other words, the error plot we have here is a combination of numerical error and the estimation error. So that may contribute to this slow decay of the relative error compared to the theory we have. So here is the summary of the talk. So the most of the items something I discussed before, so I'm gonna skip it. And what's important part is the bottom that we have derived some theoretical analysis of the convergence of the error, and we shows very interesting behavior that this error actually decays as we make the input resolution coarser. But this theoretical analysis is limited because we are looking at the isotropic flows, and the theoretical estimate we are getting is actually very conservative. So that it is interesting to see how we can expand the theory to more complex flows, and then how we can get more sharper error bound than what we currently have. So I think that that's all for now, and thank you for your attention.
Thank you so much, Kyungmin. That was a really nice presentation. Do we have any questions from the audience?
Yes, I have a question. Hi, I'm Jen from Brown, and I think it's a very interesting work. I have a question about the driven force of the observer system. Could you please turn to that
Sure.
page? Yeah, here. This driven force is on the coarse mesh, right? It's a filtered, and okay. So what you are saying is, if you add this driven force even at a coarse mesh, you can force drive the observer system to match the real data.
Yes.
Okay. So, but how? What's the initial condition of the observer system?
Yes, that's a good question. So the initial condition of the observer system is actually almost a zero velocity field. So that this is the ground truth data.
Yes.
Ground truth data has a very only have a high wave number component, right?
Yes.
And then when you average this high wave number component, you get zero velocity field because now we are averaging over 32 grid space.
Yes.
So we have very different initial velocity field from the ground truth and the observers. That's why yeah, go ahead, please.
Yeah, I mean, is a selection of the initial condition important to this method, or is arbitrary?
No, it's arbitrary because no matter where you start, eventually, if the initial condition is far from the ground truth, then we are going to have the exponential convergence towards zone of convergence.
Okay, I see.
So if you start from close to the ground truth, then probably we have faster decay. But anyway, in any cases, we are going to have the theory essentially dictates that the convergence should be exponential in time.
Yes, thanks. And another question is about the property of the noise. So now I think the noise should be zero mean, right?
Yes.
So in that case, if you take an average or filter within a small domain or a relatively large domain, the effect of noise will be nearly zero because the mean of the noise is zero, right? Is that important to the the final result? If I don't have the zero mean noise from some real say PIV measurement,
Yeah, that's a good question, and that's very true. So the basic idea is that there are two different types of information exchange. One is that we can use high resolution information, but it's highly noisy. On the other hand, if we use a large grid, as you said, we can remove almost the effect of the noise, but we are losing all the small scale informations. So there's a trade-off between these two, and the theory is essentially how to balance between these two. How to balance between having noise and then losing high resolution information. And what's the limit we can go?
Yeah, I see. So if the noise is not zero mean, maybe the trade-off is slightly different, but zero still have an optimal point.
Yeah, right.
Okay. Yeah, great talk. Thank you.
Thank you.
Hi, my name is Vivek. I'm a PhD student working with George, Professor Karniadakis. Great talk, Dr. Kyongmin. So I also have a question along the similar lines. So I understand in this case of Kolmogorov flow, you were doing the solver and you had control over the noise you added.
Right.
When you presented in the one of the earlier slides, you showed the PIV measurements where you don't have, if I understand correctly, you don't have as much control over the noise in the signal. So have you tried implementing your method on the PIV data and see how it works out?
No, that's a very good question. And frankly speaking, I do like to see it, but we really haven't done it. So we just one of the motivation we did this study is that we want to have some theoretical foundations on the super resolution method. That currently we see many of super resolution because it has potentials, but we don't really know how this super resolution will behave theoretically, whether it does have convergence properties or why it's working. So that's why we started this study. But again, as I said in the conclusion, it has many limitations, and we do like to see actually how it works out.
Yes, Dr. Kyonan, thank you. I think like you should be able, the noise you assume should be, you need to model the noise very accurately.
Right. I kind of, I kind of agree with you because in most of the real life problems, we don't really have the white noise. We usually have correlated noise, and usually we have the bias depending on, say,
Yes.
if we have the channel flow, depending on the location we see, we will have a bias, like a constant bias, right? And how it will affect the superposition reconstruction, that's to be seen. But that's to be studied, but there is a direction to further study.
Thank you. Great talk again. Thank you.
Great, thank you. Do we have any other questions?
Yeah, hi, this is Martin.
Hi,
Just
Martin.
saying hi, Kyongmin. Great talk. I only saw one's email this morning earlier, and I thought, normally I don't come to these webinars because the timing is wrong, but I saw you were talking, so I was very happy to hear what you've been doing. This is great work, really interesting. And I'm glad Vivek asked the question that in relation to this, both Vivek and Aruda Bora have been doing work with diffusion maps. So taking noisy images of turbulent flows or something, taking pictures and using neural networks, but they're losing the small scale data, and then they're using diffusion maps to fill in the gaps. But I have questions about how well that really is working, because you can reconstruct the spectra, but not really get other things, third order moments and so on. But this is interesting work because it also shows the effect of synchronization, that in some ways the 2D turbulent flow is, once you've captured the large scale features, it seems that there's some degree of slaving of the small scales to the dynamics. So it's, really revealing work. Oh, great stuff. Thank you.
Thank you, Martin. Yeah. I mean, that's already have question we also have that when you use diffusion models or other methods, it's very difficult to have a physical constraint as a hard constraint. So that it's very difficult to have a solution that satisfies the physical properties correctly. So that's something also we are currently thinking about the future research directions, that if we have a neural network or any models that can have a physical properties as hard constraints, such as momentum conservation or something. So
Great. Thanks.
Thank you.
Thank you so much. I mean, that was a really good talk. Thank you so much for your time and for joining us. So I think now it's time to move for the second speaker. Cole, are you here?
Yes, I'm here.
Great. Thank you so much for waiting. And could you please try sharing your screen?
Sure. It doesn't have anything on it, but I should be sharing it now.
Yeah, could you please share your PowerPoint? Let's see.
Sure.
Nice. Yeah, nice.
Okay,
This is
awesome.
great. Yeah, okay. So our second speaker today is called Zachry. He's an aerospace engineering PhD candidate who started working with Dr. Atlanasius Group in August 2024 at Georgia Tech. His research interest lie in the fields of computational engineering and fracture mechanics. Nicole, thank you so much for joining us this week. We're looking forward to your talk, and with this short introduction, you can start whenever you're ready.
Of course, I'm happy to be here. Thanks for having me. Hello everyone. My name is Cole Zachry, and today I'll be sharing our work on developing a mechanics-informed, model-free symbolic regression framework for solving fracture problems. So I want to start off by explaining just exactly what fracture mechanics is. Fracture mechanics is the study of crack propagation in materials. The goal of this field is to understand and characterize how cracks will grow and what conditions will cause failure in a material. Though the idea of a crack in a material is easily understood, the process for solving fracture mechanics problems can be relatively complex. Solving a fracture mechanics problem requires careful consideration of geometry and material properties. On top of this, non-standard geometries can add complexity to our problem. Adding even more complexity to the problem, new types of materials are being created every single day. As the world begins to push for sustainable materials, we must learn how to characterize their material properties. Sustainable materials such as biocomposites are heterogeneous and behave in a unique manner, while most fracture mechanics solutions were written in respect to homogeneous materials like metals. There is a growing need to analyze specimens of non-standard geometries. This need arises when specimens aren't suitable for a certain material or specimens of non-standard geometry are difficult to manufacture. Example cases of this would be if there's not enough material to manufacture a standard specimen, or if a material prevents precise manufacturing. So, our overall goal is to be able to analyze non-standard test specimen geometries used to characterize various types of materials. And we believe that machine learning could help us do this. To tackle these increasingly complex problems, the field of fracture mechanics has begun to steadily introduce machine learning approaches. These approaches have shown to produce accurate results, thus showing potential to really help the fracture mechanics field advance. Here, I will provide 3 examples of machine learning used to solve complex fracture mechanics problems. In the first figure, we see a neural network model that was used to solve reverse nano-indentation problems. So rather than extracting just from the loading stage, we can extract material properties from the unloading stage with the help of a neural network. In the second figure, we see a segment of a framework where a machine learning model was fed simulation data to predict fracture propagation in materials featuring different crystalline orientations. In this third figure, we can see a machine learning Gaussian process regression model developed to predict mode 1 fracture toughness in pillar splitting specimens. However, these machine learning methods were designed to return a numerical solution based on the input parameters. Among many types of machine learning, one stands out. This is known as symbolic regression, where when given a data set, the framework will return an analytical solution. This method has been well established and is known to be able to provide analytical solutions with great accuracy. So, the reason symbolic regression stands out is because of how it compares to other typical machine learning methods. The typical machine learning or neural network approach would return a predicted value based on a training data set. However, this creates a black box issue of not knowing or understanding how the solution was formulated. Having an analytical solution that is generalizable would be more convenient in its application since it allows us to reuse it with different input parameters at no computational expense. In other words, it would be a lot easier for a non-domain expert to use an analytical solution than to create and run an FEA simulation model or attempt to use a machine learning model. It could also be beneficial to us to know how the different parameters would relate to each other. Therefore, the obvious choice to meet this need would be symbolic regression. However, a number of problems arise with the use of an uninformed symbolic regression method when applied to fraction mechanics problems. Error can be introduced during the data preprocessing, model training, and expression selection stages. To avoid these issues and create a machine learning framework designed to better solve fraction mechanics problems, we decide to take the following approach. First, we use mechanics-informed feature engineering to preprocess our data, taking common mechanics knowledge and applying it to our problem. Next, we use a model-free symbolic regression algorithm that can check for data separability while avoiding the possibility of error introduced by model training, as opposed to the neural network approach, which does train a model. Lastly, we once again apply mechanics knowledge to select an appropriate expression. This approach was inspired by many other informed frameworks or physics-informed frameworks. So, our framework is composed of three main steps: dataset preparation, identifying candidate expressions, and selecting an appropriate expression. In the following slides, we will work through each of these steps while using a linear elastic single-edge notch beam specimen, with the goal of finding an analytical solution for the mode 1 stress intensity factor, K1, which characterizes a material's resistance to fracture. Linear elasticity is the most simple form of fraction mechanics problem. Since its stress strain behavior is linear, we can start here and it would make the most sense. Later on, we will solve a slightly more difficult problem by adding plastic behavior to the material. So step 1, dataset preparation. Determining that K1 is a function of crack length, beam height, beam span, and load for a linear elastic single edge notch beam specimen, we can run our simulations. After obtaining our dataset from running simulations, we must pre-process it to be dimensionless for the framework. We choose to do this to reduce the dimensionality of the problem and to allow our framework to focus purely on numerical relationships rather than dimensional relationships, which would force it to take the parameter units into account as well. From our dimensional analysis, we find two dimensionless terms, alpha and beta, which are the crack length and beam span normalized by the beam height. Moving on to our output, K1, we instead choose to normalize this value by incorporating mechanics knowledge. We know the analytical solution for the average stress in an unnotched beam, so we can then normalize K1 using this value along with the beam geometry terms to get our normalized stress intensity factor as a function of alpha and beta. From there, we can move on to step 2, which is identifying candidate expressions. After pre-processing the dataset, we input the data to the symbolic regression algorithm. Our algorithm then checks for additive and multiplicative separability. Once the data has been fully separated, it begins symbolic regression on the separate datasets through polynomial fitting and brute force methods, and then returns a list of candidate expressions for each separated dataset. Before we continue, I would like to talk about what separability means in this context and how we check for it. So, what is separability? Imagine we have an unknown function of 3 variables, x1, x2, and x3. Now consider we could decompose it into multiple functions of lower dimensionality that operate on each other as so. These lower dimensional functions are a lot faster and easier to find using brute force and polynomial fitting. In other words, telling our framework to process our full dataset would be like telling someone to eat a cake whole, while separating our dataset would be like eating the cake one slice at a time. That is what separability is. So, how do we know if we can separate our data? Our framework will calculate the error produced by the separation. If that error is below our predefined threshold, then the dataset is considered separable. Let's say that we want to check our K1 function, if our K1 function is really just a function of alpha plus a function of beta. Here, the column of alpha values in our dataset will be referred to as the I dataset, X sub I. And then the column of the beta values in our dataset will be referred to as the J dataset, X sub J. We would then calculate the additive separation error through the following equation. Now, this is a rather large equation, so let's take some time to break it down. In this equation, P denotes the row of the dataset, and N is the total number of rows in the dataset. As stated previously, I and J denote the two separated datasets. The terms Ci and Cj are constants that refer to the mean values of their respective datasets. In this case, separating alpha and beta, Ci would be the mean alpha value, and Cj would be the mean beta value. Therefore, the black term is the pth y value of the original dataset. The blue term is the y value that corresponds to the pth x value of the I dataset and the mean values of the j dataset. The green term is the y value that corresponds to the mean value of the I dataset and the pth x value of the j dataset. And lastly, the pink term shown is the y value when all variables are the mean value. This term can also be called the recovery constant and serves the purpose of preserving the fidelity of the data when separated. Similarly, if we want to see if K1 is just a function of alpha multiplied by a function of beta, this is how we would calculate our separation error for multiplicative separation. We can see here that all the terms are the same as in the additive error equation, just operating on each other in a way appropriate to multiplicative separation. Due to the nature of our separability check and error equations, two requirements are imposed on our dataset. The first one being that the dataset must include the mean value of each variable. For example, if x1 has a range of 1 to 5, then x1 must include a value of 3. The second requirement is that the dataset must be made up of every possible combination of values. If either of these requirements are not met, then the framework will not be able to run successfully. Lastly, if both additive and multiplicative separability are found, how do we know what to do? So imagine the error for both types of separation was found to be below our threshold. Our framework will then choose to execute the separation that creates the least error. Shifting the topic back over to the three main steps, we can now enter step 3. Once the framework is done running, we obtain a list of candidate expressions for each separated dataset. We then assemble every possible combination of candidate expressions, which results in an extremely large list. To narrow this list down, we first choose to exclude expressions with a mean absolute percentage error above 3% with respect to our original training dataset. Next, we apply mechanics knowledge again to select our combination of candidate expressions. We know that for a short crack in a slender beam, the normalized stress intensity factor should be 1.12. We will edit our input values to recreate this condition so that alpha would be very small and beta would be very large. That way, we can test our list of combinations to see which combination yields the closest value to this. For the linear elastic case, we have found that our framework produces significantly less error than other comparable symbolic regression methods and has the potential to produce a generalizable solution. In the figure shown, we tested our found equation within an extended parameter space to show this. So now that we're done with the linear elastic fracture mechanics case, let's move on to our next problem involving elastic plastic materials. In the previous problem, we used our framework to find an analytical solution.
Can I ask you a question? This is Suku from Davis.
Excuse me?
I have a question for you from the previous topic.
Sure.
Yeah, so I mean, have you also compared with, for example, handbook solutions of Tara Paris and others to see the range of values that you can get and how close they are to that?
Yes, in our paper, we did compare to two analytical handbook solutions. I believe it was Brown's and Schwally's.
Okay. Also, in your symbolic expressions, you only have polynomials, right? In the end, either they could be separable, basically separable form, right?
Exactly. So we do have polynomial expressions for each separated data set. And then we reassemble them back together as a combination.
So is there a possibility of like using exponentials, for example?
So far we don't have
Or fewer
a
exponentials,
separate
essentially, like a fewer exponentials in some sense, right? Because they can capture, Taylor series is the whole expansion of polynomials, right?
do you mean like a exponential, like a function to the
Right.
power of a function?
Yeah, exponential.
Or like
Well,
the
exponential of say
exponential
alpha x or
mathematical.
like ax, right? With different a's, basically.
Right. I don't believe that our framework checks for that, but that could definitely be something we could look into to further improve upon.
No, because I was wondering how high do the polynomials go to? That's why I was thinking.
Oh, I see. Okay. Sorry,
Yeah.
I misunderstood your question.
Okay.
Yeah, so how high do the polynomials go?
Like what degree? I mean, like degree.
Yes. I don't have an answer for that, unfortunately.
Like in the ballpark of what? I mean, is it 100 or 20 or 10 or?
I would say they increase to be rather complex. So that's a good question. I would love to get back to you on that.
Yeah, because ultimately, you're using symbolic regression, but you're using polynomial as a library, sort of, right, to construct your.
Yes.
Yeah. Whereas in neural networks, obviously there are more complicated functions which are composed of, based on the activation function, right, and so on and so forth. So of course there is, but here you're sort of fitting, you're already pre-selecting the functions you want to use, right, basically.
Right. I do know our expressions do go up pretty high in terms of complexity.
Right.
So I just don't have the exact answer off the top of my head.
No, because I was thinking that, when you go to very high order polynomials, then stability also is an issue of computing them and all those issues, right? So
Right.
So I was just curious about that, right? Yeah. Okay. Anyway, thanks. Go ahead. Yeah.
Okay. So in the previous problem, we used our framework to find an analytical solution for a linear elastic problem. Now we want to add plasticity to the problem, which adds a nonlinear region to the stress strain behavior. In the second figure shown, we can see that the stress strain behavior is linear up until it reaches a stress value known as the yield stress. Once the value is surpassed, the stress strain behavior suddenly becomes nonlinear. If a material's behavior follows this general curve, it is known as a Ramberg-Osgood obeying material. We want to use our framework to find analytical solutions for these types of materials. The Ramberg-Osgood equation shown can be manipulated in a way that gives us an expression for the total strain and reveals the elastic and plastic strain terms in this expression. However, the material constant shown as C can be difficult to determine. Considering this difficulty, we apply the 0.2% offset method, which assumes that the yield stress occurs along a linear path defined by the Young's modulus starting at 0.2% strain. When applied to Ramberg-Osgood, we obtain an expression from which we can use the plastic strain term in our simulations to define the nonlinear behavior. For Ramberg-Osgood obeying materials, the quantity we are interested in finding an analytical expression for is known as the J integral, which defines the energy required for crack growth. We are able to define J for a single edge notch beam specimen as a function of load, crack length, beam height, beam span, Young's modulus, Poisson's ratio, yield stress, and the material constant N. Now we will go through the steps of our framework again, this time for the plasticity problem. Back to step 1, dataset preparation. Following the same approach as last time, we obtain a set of dimensionless variables from our dimensional analysis. Alpha, which is the crack length normalized by the beam height, beta, which is the beam span normalized by the beam height, gamma, which is load normalized by Young's modulus and beam height, Poisson's ratio, which is already dimensionless, yield strain, which is yield stress normalized by Young's modulus, and the material constant N, which is already dimensionless. So our normalized J is a function of these dimensionless variables. Once again, rather than normalizing J in a conventional way, we will apply mechanics knowledge. We know that in the linear elastic regime, J is equal to the energy release rate. We can then choose to normalize our plastic J by the linear elastic energy release rate. We choose to do this since it's the most relevant term to our output, even though it is defined by linear elastic behavior. Moving on to step 2, we can run our data through our symbolic regression algorithm and identify candidate expressions. Upon running the framework, we can see that each term in our dataset has been considered separable in the displayed convention, where the plus sign represents additive separation and the multiplication sign represents multiplicative separation. To figure out how to reassemble the separated datasets, we must decompose the full function into the separated functions, following the same order of separation and applying the recovery constants in a manner appropriate to the separation time. So, for the first separation, we separate our function of alpha through additivity while applying the recovery constant. For the second separation, we separate our function of beta through multiplicativity. For the third separation, we separate our function of gamma through additivity. For the fourth separation, we separate our function of nu through multiplicativity. And for our fifth and last separation, we separate our functions of yield strain and N through multiplicativity. We can then assemble our separate candidate expressions back into the full expression using this last equation shown. Now we move on to step 3 and select an appropriate expression. To select an appropriate expression, we follow the same process as last time. We will first assemble every possible combination of expressions and exclude all expressions that produce an error greater than 10%. This is different than the last case since we now have a higher dimensional problem, so therefore we can expect more error. Next, we will apply mechanics knowledge to find our final expression. We know that when in the linear regime, our normalized J should be equal to 1. A case where Ramberg-Osgood obeying material behaves linearly is when yield strain is when a Ramberg-Osgood obeying material behaves nonlinear is if the yield strain is surpassed. Therefore, we want a case with low load, high stress, and N to equal 1. Inputs that could replicate these conditions are gamma equal to a very low value, such as 0.004, a relatively high stress, such as 0.001, and N equals to 1. After applying the criteria in step 3, this is the final expression we are left with, where these are the separated functions of alpha, beta, gamma, Poisson's ratio, yield strain, and N. Plugging them all into the final assembled expression would result in a very large equation, so I left them separated. But to assemble, you would plug them into this formula. Testing the error of our expression, we get a 9.6% error within the training space. While seeming higher than nominal, this is likely relatively low considering the high dimensionality of the problem. In an extended parameter space, we have been able to achieve a 6.31% error so far. I would like to point out that we were only able to obtain a handful of convergent results in the extended parameter space, possibly due to the weird combination of material properties leading to a lack of convergence. In the future, we would like to perform more simulations in the extended space to get the full picture. Nevertheless, this low error furthermore goes to show that our framework is capable of formulating analytical expressions for complex fracture mechanics problems that are both accurate and potentially generalizable. This is extremely important to the field of fracture mechanics since we now have a reliable machine learning method to produce analytical solutions which can be reused at no computational cost and can be used by anyone. We have shown now that our framework can find an analytical solution for a simple linear elastic problem and a slightly more difficult elastic plastic problem. So in summary, our framework can provide easy-to-use formulas for unconventional fracture mechanics specimens, therefore removing the need for complicated FEA simulation or the use of oversimplified empirical formulas. Additionally, we can look to these formulas for potentially generalizable relationships between material properties and geometry. Here's the paper published on this framework for anyone who would like to read more about this. Thank you all for listening. I would now be happy to take any questions from the audience.
Thank you so much, Cole. That was a really good talk. Thank you so much for sharing your insights with us. Do you have any questions from the audience?
Yeah. Hi, my name is Vivek and I'm a PhD student working with Professor Kaniadakis. So I have a question. So are you able to predict or estimate the path of the propagation of the crack? Or I didn't get that part.
Our framework isn't necessarily predicting fracture propagation path, like in
Okay.
terms of like how a crack will grow.
Yeah.
We're more or less trying to find analytical solutions for fracture mechanics quantities that would tell us, for example, K1 in the linear elastic case, it tells us how resistant a material is to fracture. So it can tell us if we could maybe use a material for a certain application and be worried about fracture or less worried. Meanwhile, the J integral in the elastic plastic problem, it characterizes the energy required for a crack to grow. So if it's almost like how yield stress denotes the beginning of a plastic deformation in a material. J integral sort of tells us if a crack is likely to grow based on the energy release rate.
Okay. Thank you.
Yeah.
Thank you so much, Cole. Do we have any other questions from the audience? In that case, maybe I have a question. Can you go back to the expression where you were saying, identifying like how to define if they are separable or multiplicative? You had like this kind of weird expected value.
Sure. Let me see. So I think it was this one.
Yeah. One question: do you have any intuition like why this holds?
Essentially, what we are trying to do is to see how I'm losing the word. I guess coupled these two variables are to each other. So in a sense, we're testing to see if a function like the y value or the difference in y values whenever we try to sort of separate the two variables one another, like how much they vary, like how much the variation between the two variables has an impact. If that makes sense. So we're more or less testing the error of like could the y value of the xi value operating on the y value of the xj value, does that produce above like a 0.005% error? So
Okay, so this one is like an error measurement in some sense, right? That's what you just said, right?
sorry, say that again.
So this one is somehow some way that you're trying to measure the error, right? Like
That's exactly what this is. Yes. So I'm not sure if I stated that, but if I didn't, yes. So this is this is essentially an error equation where this E add here represents the error caused by additive separability. And if this error is below our predefined threshold, then we can consider the data sets to be separable.
Oh, nice. And do you have any like reference how did you guys found this equation? Because it's quite interesting. It's I think that it's quite interesting, and it may be interesting to know how did they kind of somehow came up with that, because yeah.
Sure. A lot of like, so this specific equation was more or less inspired by AI Feynman's separability check.
Oh, okay. I see.
So
So wait, so inspired by AI Feynman, so they then got this expression using AI Feynman, or was one of the
no,
equations that
so
were
they used it to check for separability, but they also trained a neural network to check for separability as well. So
Hmm,
when I say inspired, I mean there's a slight difference in the fact that they also depend on a neural network while we depend purely on this equation instead to
I see.
remove the need for a training model.
Oh, okay. I see. Okay. Do we have? Thank you, Cool. Do we have any other questions from the audience? It looks like we do not. So I think that with this we can close the seminar. Thank you so much, Cole, and for your time today. This was a really nice talk. And thank you everyone for your time this week. And I think that now we can close this session, and until the next time.
Well, thank you so much.
Bye.